Welcome to lesson 22. So far we have learnt about the basic functioning of a PLC, we have learnt how to write a program for it, but all this time we have seen the PLC as an abstract device. We have not seen what is inside a PLC system, what actually physically makes it. So, in this lesson we are going to look at the hardware environment of the PLCs, basically what PLC systems are made of, right. So, we are going to look at components, we are going to look at components of the PLC system, their architecture, by which I mean that how they are organized, how they are connected, and their functionality, that is describing what they do. Okay. So, now let us see. Before we begin, it is customary to see the instructional objectives. So, the instructional objectives are the following. First, after going through this lesson, one should be able to mention the distinguishing features of industrial automation computational tasks. A PLC basically is a computer. So, it performs computational tasks related to industrial automation, but these tasks have certain very distinguishing features compared to the other tasks which are, let us say, done in an office environment. So, we are going to, you should be able to mention some of these features, mention major hardware components of a PLC, describe major typical functional features and performance specifications for the CPU, central processing unit, IO or input output, MMI, the man machine interface, and communication modules. Okay. Then explain the advantages of a function module. So, what are the advantages of a function module? You will be able to explain, and describe some major typical function module types. So, these are the instructional objectives. So, let us start with the industrial automation tasks and their distinguishing features. So, we are going to look at the nature of industrial automation, what I call IA computation, that is computation related to industrial automation. These kind of computations, remember, that are always working on physical signals, right. So, there are temperatures and pressures and limit switch positions, starter positions, etc., which are all very physical signals, electrical in nature, which are interfaced with the PLC, and the PLC looks at its values and takes some of these as inputs and computes the output, which it computes according to some its software, for example, relay ladder logic programs. Okay. These tasks requirements are by standards of other applications using computers, let us say digital communication or personal computing. These tasks are the computational requirement of these tasks are generally called slow, are generally should be slow, although among themselves there could be tasks which are very slow. For example, temperature control tasks are very slow, having time constants of the order of minutes. Let us say flow control tasks would be faster, and if you have a machine control, or you have to have an actuator control, electromechanical control actions. So, in such cases the tasks are relatively faster, but even those, basically they are all made of to move an electromechanical system with a certain finite amount of power generally requires times of the order of milliseconds, or at most a fraction of a millisecond. Before that, no perceptible motion will be produced. On the other hand, these speeds are much slower compared to the speed of electronics, which we typically encounter in, let us say, communication systems. So, in that sense they are slow, although within their own categories there can be fast tasks and slow or medium fast tasks or even slow tasks, right. So, that is what I wanted to mean when I wrote slow fast. The complexity of these tasks are also not very complex, some of them are very simple. Relay data logic diagrams are often very simple, but there could be other complicated control algorithms, there could be self tuning algorithms which could be somewhat complicated. So, I would say that the complexity of these tasks are low to medium, not highly complex. Interestingly, many of these tasks are repetitive. For example, if you take a standard process control loop, then every sampling time you have to input the control variable and based on your control law sense the set point and then compute the manipulated variable, right. So, this computation of the manipulated variable and inputting the set point and the control variable goes on repetitively. So, these are generally repetitive tasks and they are real time. Any computational task is called real time when there is an explicit time boundary by which this task should be completed, and this fact is actually taken into the design of the computational system which is supposed to perform this task. For example, in a control loop, whatever computation you are having, that should be completed within a sampling time. So there is an associated deadline for completing these tasks once they are started. So you in other words, even if you have a very grand control algorithm which takes a lot of time and does not complete within a sampling time, is not at all suitable, rather probably a less grand control scheme which will complete within the sampling time will be preferable, right. So, in that sense they are real time, and for real time tasks one has to, because you have to also realize that within one PLC there will be several control loops working, either rungs, either they are discrete sequential control or they are analog controls, whatever it is, there are a number of control laws which have to be repetitively executed, right. So, there is a requirement of determining that which should be run at what time, because some of them will have to be run, let us say, every 20 millisecond, some of them may have to be run every 500 milliseconds, some of them may have to be run every 2 minutes, right. So, this is called scheduling. So, there has to be a mechanism of scheduling tasks at the appropriate time, so that computational resources are utilized and all the tasks are finished at before their deadlines. Okay. So, this is generally done using technology called scheduling, and we will not go much into that because that is in the domain of real time systems, but generally in the case of PLCs, even when there are scheduling, PLC schedulings are generally very simple and they are static in the sense that they are the strategy which is adopted is fixed, it does not change according to situations generally. Similarly, they have very rudimentary kind of operating systems, much less generally much less sophisticated than standard other operating systems like Unix. Apart from that, but one thing is very interesting, that when you have a PLC, I mean these computational tasks are very mission critical in nature, in the sense that we do not want to have any kind of errors in them. So, they should have very good reliability and they should always ensure worst case performance specifications. We cannot check average case performance specifications, like for example, if you have Ethernet, then we know that Ethernet worst case performance is generally very, I mean goes down significantly compared to its average case performance. So, but here whatever technology we are using, we should generally always use worst case performance as the performance guarantee, because the consequences of a task failure could be very great, right. Lastly, often it happens that this computational environment computational tasks have to be performed at very harsh physical environments, having a lot of dust, heat, moisture, vibrations and such things. So, the hardware has to be such that it is not affected by these. One has to devise proper sealings, one has to devise proper cooling mechanisms. These are also very important in the case of industrial automation computer systems to ensure that the tasks are performed reliably and as expected. So, having said that, let us look at what makes a PLC. So, as I have said that a PLC is basically a microprocessor based system. So, as we know that a microprocessor based system will have the major components are number 1 CPU, number 2 memory, number 3 input output, number 4 power and number 5 the buses, right. So, here also you will find basically the same things. So, here you have the CPU, this is the CPU and here is the memory. As we will see, memory can be of various types and you will find you can easily make out that the PLC applications are very rich in I/O, because their basic job is to interact with the physical world, right. So, you have various kinds of I/O. For example, you have analog I/O, you have digital I/O, you have remote or sometimes called distributed I/O, you also have network communication, much of it is again I/O. So, you have various kinds of I/O, you have man machine interface which is also a kind of I/O, input output. Then you have a programmer by which you can develop a program let us say an RLL program, and you can load it into the PLC memory, that is also a kind of I/O. Then you have power, you have the backplane, that this is the bus which connects the various PLC elements. Sometimes you must be knowing that sometimes you have other processors which assist the main processor. So, you could have a this is not common, this is wrong. What I meant to write is a communication processor, right. So, please correct this, by which I wanted to mean that this is a communication processor, because it has to a PLC has to sometimes communicate with special purpose devices. So, that job is often given to a separate processor. Similarly, it could have separate input output processor, it could even have a network processor. In fact, a communication processor, part of the job is to do communication, maybe on the network environment also. Sometimes you have separate, these are actually I/O which are intelligent in the sense that they have their own computing capabilities. So, one needs to so the main CPU needs to talk to it. So, therefore, this is also a kind of I/O. So, you see that a PLC is basically a microprocessor based system with a lot of I/O, and we are going to see what these different types of I/Os are. So, let us look at these modules at some level of depth now. Okay. So, you have a processor, a typical processor would be, I mean this is just an example, it could be 80186, it could also be from the 68000 line, various choices are available. Sometimes these processors are proprietary, not standard processors. Along with the standard processor, as I said, you could have coprocessors for specific purposes like I/O, like handling the programming input, etc., or managing the network. You obviously have RAM is required for running it. You have sometimes you have dual ported RAM. Dual ported RAM is RAM in which simultaneously it has 2 ports, So, it can be simultaneously written into and read from. Okay. This is important, especially when you want to read data from devices which are working without really stopping the device operation. You want to read data or you want to write data. So, you can on the fly parameterize, dump some new parameters for a PLC while the PLC is working. So, the PLC continuously uses its memory, but in between when during those brief instance when it is not using the memory, if you have a dual ported RAM, then using another processor you could write the same memory and download your parameter values in the meantime into the memory, which the PLC will use as it gets them. Okay. So, this kind of reading and writing on the fly by another processor is possible if you have dual ported RAM. You have EEPROM or E square PROM. These are typically read only memories and they are used for storing the PLC programs. You have programmer ports which are used for downloading programs. You have network ports. You have backup battery. This is very important, because by any chance if you have power failure, you do not want, number one, your process state to be lost, number two, you do not want to lose your parameters. So, there is a backup battery always which will back up part of the RAM, and you obviously need the power supply which could be internal within the processor module, or it could be external as a separate power supply module which will connect to the processor module. It could be either way. So, let us look at a typical PLC system, a picture which will clarify the things. So, here is a typical PLC system. So, you can see that it contains multiple CPU units. Actually, these are, if you look at them, these are the various CPU units. Okay. So, these are the CPU units. Some of them are communication, some of them could be communication processors or other coprocessors. One of them will be the main processor. There are a number of rack mounted IO modules. So, these are the rack mounted IO modules, IO racks. Each one of them will plug in one particular IO card which will have various, which will interface a number of IO signals, and you have the power supply here, right. So, this is how it typically looks. You can see a number of ports. So, for example, you have a number of ports here, right. So, these are probably the communication processors. We can't, because they are having so many RS 232 ports, serial ports look like. There are some parallel ports, looks like printer ports. So, this is how a PLC actually looks like. There are actually, this is not the only type. PLC systems could be very large, they could be very small, everything comes into one box, that is also possible. This is a medium range kind of application. So, having looked at that, let us see how these various things are schematically connected. We just saw a diagram. So, you see that this is the scheme in which these various processors and the modules are connected. They are all connected by a bus. This is, and obviously as you have seen that various IO modules are mounted in racks. So, there will be a ribbon cable like thing, there will be a flat cable which will act as this bus, it will connect the various modules, and sometimes these modules can even may not be situated at the on the same row. Sometimes they will be connected one after the other, sometimes they may be connected in a cabinet which is a little distance away. So, this bus really has to extend sometimes using cables also. So, you have central processor, various kinds of coprocessors, IO processor. Nowadays we are having the age of embedded processors. So some of these processors are use even DSPs. So there could be numeric coprocessors or IO processors. Generally there are communication processors for specific communication to kinds of devices like operator stations or for communication on the network. There are various kinds of IO modules. Some of them have processors on them, so they are called intelligent IO. Some of them are ordinary IO, which just takes signals and feeds it to the central processor. Plus there are obviously memories. So this is the basic hardware architecture, which is very common for microprocessor based system. They are generally organized around a bus. Oops. And if you see inside one processor, that is also pretty standard, in the sense that you have, as you all know, that all microprocessor based systems have two kinds of buses. One kind of bus is called a data bus, another kind of bus is called an address bus. So using address buses we can talk to specific devices and then we can exchange data over the data buses. So these are the data buses, connects to various devices, and these are the address buses by which the devices can be selected. You have the main processor, you have various kinds of memory. You have application memory where the computational tasks run. Even for running tasks you need a for managing the resources of the PLC you need some programs which are typically called systems programs. So for that you need systems program memory, you need systems data memory. You have special kinds of PLC systems are just like you must have experienced that sometimes your PC hangs, it just sits quiet doing nothing, somehow it gets mired into some infinite kind of loop. So this is prohibited in PLC systems if due to from reasons like wrong programming to memory memory corruption. If the processor stops doing useful work, then there has to be explicit mechanisms by which the processor execution must be brought out of it and taken into a safe state. So this is typically done by watchdog timers, which are hardware devices, and sometimes they are also they are actually hardware devices, and if these timers find no proper activity over certain periods of time, then they by force take the processor to some safe state. Okay. So you could have dual ported RAMs, as I said, apart from the normal RAMs. Obviously there has to be various kinds of interfaces. Sometimes here they have shown, here we are seeing a particular another additional processor. See, this is the main processor, but we are seeing an additional processor, and the job of this processor is to interface with the programmer, so that you can, while this system is working, a PLC system is typically interfaced with the machine, and industrial machines often run continuously. So you must provide mechanisms excuse me, so that you are able to load new parameters, read status, you are able to work with the system while the system is working with the machine, so without stopping it. So for that, since not only you need a dual ported RAM, you need another processor which will talk to the programmer while the main processor is actually busy controlling the machine, right. So this is what is done. So typically these processor modules, though this is mainly a discussion on hardware, we would like to mention that typically these processor modules come with some pre-programmed software, minimal pre-programmed software. More than that, one has to develop, or one has to take from additional libraries. So you have standard things that some standard things are supported, like for example basic counting timing functions, some software up down counters, quite a few of them actually, from 0 to 999 typical value, and several timers which can time durations of the order of milliseconds to of the order of several hours or even sometimes days are available. You have various standard control algorithms already pre-coded, so that the users do not have to can easily configure their systems. The program execution in these systems is very interesting. There are generally 3-4 different types of program execution modes specified. For example, a mode could be cyclic. By cyclic we mean that you have a number of computational tasks begin just like RLL program execution. So, begin here, come to the end, start all over again. So, this just goes on. Typically cycle time remains more or less constant, but it could vary a little bit depending on the program logic. For example, if you have some program control statements, if then else kind of statements, then whether some block will be executed or not will actually depend on the data. So, program execution time is not always constant, it actually depends on data, but roughly it will be constant, and in fact it is preferable that it is constant, so that you are not surprised that for some value of data suddenly your program execution takes a very long time and your deadlines are missed. So, it is preferred that real time programs have predictable and not too much varying time requirements. So, for many classes of applications cyclic is good enough. So, that is the simplest. Apart from that, you could have time controlled executions, where certain operations will start after certain times, either absolute times or relative times, that is start the pump after 30 seconds of opening the valve. This kind of controls can be executed. So, exactly 30 seconds after. So, this execution is timer controlled or time controlled, or it could be interrupt driven. There are some tasks which can suddenly occur, like failures kind of tasks, which once they occur they are not taken into the consideration of the regular computing flow, but once they occur they are required to have very high probability, very high priority, I am sorry, and therefore they have to immediately get the attention of the processor. So, such tasks are sometimes coded in the interrupt driven execution mode. So, whatever the processor was doing, it will be interrupted and this requirement will be catered to. So, but all said and done, for a given, I mean typically one must understand that typically a PLC has much less computational capability compared to a PC, although it is generally much more expensive, or that is if you take PLCs and PCs of the same kind of price, then you would find that the PLC is much less computationally capable compared to a normal PC which sells in the market, both in terms of memory and in terms of computing speeds. That is because price of things get actually decided by the sales volume, plus the PLC has certain other features, they are actually very rugged and they are different kind of packaging. So, all these things make this, and the third reason is that a PLC is not a general purpose computer. So, no one is going to download nice files from the internet and store it there, and then your emails keep piling up. Such things do not happen. So, therefore, memory requirements are generally well understood and much less than what is required. So, therefore, one keeps things only which is required, because one wants to make things reliable, and putting too many things into a machine makes it unreliable, right. So, but one has to understand that these are, although they are much like PCs, in fact there are in the market the competitors of PLCs are actually called industrial PCs, which are really PCs, run on run on similar operating systems, Windows, some versions of it, but they are actually, they have generally much lower computational capabilities.